Welcome once again to Control System Lectures. This video is a continuation of the one that I did on the Introduction to the Routh Hurwitz Criterion, which if you missed, you can click on this link here to watch. But at this point, we already know the basic fundamentals for how to set up and populate the Routh Array. So in this video, I want to describe two special cases that can arise when you're filling it out. But before I begin, I want to just blaze through a quick example on how to set up and fill out the Routh Array. This is just a recap from the last video. Let's say you're asked to determine the stability of a system who has a characteristic equation that is s to the fourth plus 2s cubed plus 3s squared plus 4s plus 5. Since this is a fourth order polynomial, you can set up the Routh array by starting with the first row at s to the fourth and ending with the last row at s to the zeroth, or 5 rows total. Now you can populate the first two rows by starting with the highest order coefficient and zigzag up and down, adding each coefficient of the descending powers of s. And at this point you can start filling in the rest of the table by remembering the figure 8 method, or 2 times 3 minus 1 times 4 divided by 2, which is 1. And to move to the second column, it's as simple as just stretching out that 8 and performing the same steps. 2 times 5 minus 1 times 0 divided by 2 equals 5. And when you reach the end of the columns, you can move down to the next row and start it all over again. And once the entire table is filled out, you can count the number of roots in the right half plane by counting the number of times the sign changes in the first column of the table. In this case, there are 2 roots in the right half plane because the sign changes once between 1 and minus 6 and a second time between minus 6 and 5. Therefore, this system is unstable. Alright, enough of the recap. Now let's get into the two special cases that I mentioned that you can come across when filling out a Routh array. The first case is when there is a 0 in a row with at least one non-zero element appearing later in that exact same row. Let me show you a few examples of what I mean by this. Say you were given a polynomial whose coefficients created the Routh array like this. In this case, there's a 0 in the second column of the first row and a non-zero, or a 4, in the last column. So this meets the criteria for our special case. Now in the second example, the first column has a 0, but it's also followed by a non-zero element. Same exact thing. Now when this occurs, the system is always unstable, because completing the Routh array will always result in a sign change of the first row. And so if you're only attempting to assess stability of the system, then you don't need to complete the rest of the table at this point. But if you're interested in the number of roots located in the right half plane, then you can complete the table like this. But first let me rewrite that second example a little bit bigger over here. So when you come across a 0 followed by a non-zero like we see in this third row, you replace that 0 with the Greek symbol epsilon. Complete the array using epsilon in its place. And once you finish completing the table, you can just take the limit as epsilon goes to 0. In our case, the first 2 rows don't change at all. The third row, that 0 becomes epsilon, which is ever so slightly positive, so I'll write that as a 0 plus. Then, in the fourth row, this can be rewritten as 4 minus 10 over epsilon, and so as epsilon goes to 0, this tends to go to negative infinity. And now in this system you can see that we still have 2 unstable roots, or 2 roots in the right half plane. Now if you don't mind, let me just quickly go into an unnecessary side note on why we use the Greek letter epsilon. In several branches of mathematics and computing, epsilon is used to represent an arbitrarily small number. So if you think of the smallest number you can, epsilon is even smaller. However, it is still greater than nothing. In computing, where numbers are represented digitally, machine epsilon refers to the rounding error in floating point arithmetic, and therefore the smallest number that can be represented on a computer before being wholly consumed by rounding error. For double precision arithmetic, which many computers run with, the machine epsilon is 2.22 times 10 to the minus 16th, so that's a pretty small number. Okay, let me show you just one more example of this. Starting with this polynomial, s to the fourth plus s cubed plus s squared plus s plus 1. We can fill out the Routh array just like we did above. But now you can see that in the third row, the first column is a 0, and the second column is a 1. And this satisfies our condition for the special case, and it also states that this system is unstable. You can say that instantly. But we still want to know how many roots there are in the right half plane, so we replace the 0 with epsilon and continue filling out the array. And when we take the limit as epsilon approaches 0, the fourth row becomes negative, the fifth row becomes positive again, proving that this system has 2 roots in the right half plane. And that seems simple enough, right? Well, let's take this one step further. The second special case is when there is an entire row of zeros, and not just a single 0 in the row. I'll demonstrate this special case and what to do with it with this polynomial. S to the fifth plus 2s to the fourth plus 6s cubed plus 10s squared plus 8s plus 12. And let's fill out the Routh array by populating the first 2 rows, and then we'll populate the other rows using our figure 8 method. But when you get to the fifth row, or the s to the first power row, that one becomes all zeros. Now before I explain how to continue filling out this table, I want to just address what this means, as there are only a few root locations that can cause a row in the Routh array to be all zeros. When you come across this, it means that you have a polynomial with roots in one of 3 situations. Either you have 2 real roots that are equal and opposite in sign, you have 2 imaginary roots that are complex conjugates of each other, or you have 4 roots that are all equal distant from the origin. You can see that in all 3 situations, they're just a reflection about both the real and the imaginary axis. Now here the first and third root patterns both have roots in the right half plane and are therefore unstable. Only this pattern in the middle has roots that are not in the right half plane, but since they exist on the j omega axis, the system is marginally stable. So when you encounter a row of all zeros, at a minimum you can assert that the system's marginally stable, but it's possible that it's unstable. Now you can determine this by completing the rest of the table in this manner. Call the row directly above the row of zeros the auxiliary polynomial. Well, technically these are the coefficients of the auxiliary polynomial. To find the powers of s that go along with them, begin with the power of s that starts the row, and then skip every other power until you reach the end of the row. For example, the auxiliary polynomial coefficients are 6 and 12, and since the row is the s squared row, you would write the auxiliary polynomial as 6s squared plus 12, or you can simplify it by dividing out 6 to just be s squared plus 2. And for simplicity, I'm going to call this auxiliary polynomial p. Now take the derivative of this polynomial p, and you can replace the row of all zeros with these new coefficients. In this case, the derivative is 2s, and you can replace the row of all zeros with this. So the first coefficient is 2, and then there are no other coefficients afterwards, so the rest of it is just 0. Now you can complete the table, which is just 2 times 12 minus 6 times 0 divided by 2, which is just 12. And since there are no sign changes in the first column, you can conclude that there are no roots in the right half plane, and therefore this system must have some number of roots on the j omega axis, or this second situation. But we can take this one step further still. If and only if there is a row of all zeros in your Routh array, then the auxiliary polynomial exists, and that auxiliary polynomial divides into the original polynomial with no remainder left over. That means that this is a factor of the original polynomial. So I can write this in an equation like this. The auxiliary polynomial p of s times some other polynomial equals the original polynomial q. And this is powerful in determining how many roots exist in the left half plane, the right half plane, and on the j omega axis. We can find what this r is by doing polynomial division. Or in other words, we can take q of s, divide it by p of s, and you'll get r of s, or the remaining polynomial. So let's start with our original polynomial, which I've copied here, and divide it by s squared plus 2, which is the auxiliary polynomial. Now at this point I'm going to skip through this part pretty quickly, since I'm assuming that most of you know how to do this division already. However, if you don't know how to do polynomial division, or you've never seen this before at all, I've worked out this entire problem without skipping any steps, so hopefully you can just play this part slowly to figure out exactly what I'm doing. You can see that we're left with a polynomial r of s with no remainders left over, and that means that both r of s and p of s are both factors of q of s, or our original polynomial. Now remember that this is only true if there's a row of zeros in your Routh array. Otherwise you'll be left with some non-zero remainder. Now at this point we can state that any part of the Routh array that is above the auxiliary polynomial goes with our other factor r of s. And since there's no sign changes at that point, we can state that r of s is a stable polynomial. And the number of sign changes after the auxiliary polynomial predicts the number of roots in the right half plane for the auxiliary equation. And this is going to go a long way towards determining where the roots exist, which we know from our three situations above that the auxiliary polynomial is marginally stable. But since we factored this a little bit, we can now solve for those roots directly from the auxiliary polynomial. In this case, the roots are at plus or minus the square root of 2 times I, which are two imaginary roots that are complex conjugates of each other. That is, that they exist on the j omega axis. And this is exactly what we expected from our situations that we wrote out above. All right, let me just summarize real quick so that hopefully it's a little bit easier to remember. In our first case, where we had a 0 in a row with some non-zero element following it, when we got to that row, we replaced the 0 with epsilon, then we completed the table using epsilon in place of 0, then we took the limit as epsilon went to 0, and then we counted the number of right half plane roots. But we also knew that this was unstable right from the beginning because we had that 0. In the second case, where we had a row of all zeros, we assigned the row above it as the auxiliary polynomial p. Then we took the derivative of p with respect to s, and we replaced the all zero row with that derivative. Then we just completed the table as usual, and then just assessed the stability of the system, either unstable or marginally stable. Now, at the risk of boring you too much with Routh Hurwitz criterion stuff, I just want to do one more video on this topic. But instead of just how to fill out the table, I want to talk about the practical uses of this method. So look for that next week, and that should round out our discussion on this topic. Also, a number of you have requested several topics in the comments section, like PID control, Nyquist plots, modern control theory, and so on. Now I want to tell you that I'm going to cover each of these topics and more, eventually. But since I only do videos once a week, it may take many months to cover everything, so please stay with me. And as always, I appreciate the feedback, both positive and negative. And if you have any comments, suggestions, or questions, please keep them coming. Thanks again, and I'll see you next week.